Alright, welcome back to the logic slides. Let us finish them up, and then we will start some new slides on proofs. So we have a whole lot more to talk about. This was kind of like the best slide so far. It's just like a big combination of all the stuff that we've been doing. This is a real proof. This is, well, if I can keep it all on one slide, this is starting somewhere and ending with the conclusion you're trying to conclude using rules of inference. That's a really strong idea. It's using proof techniques to get from some starting points to a finishing point. Okay, so let's do some more of that. Here is an example. I'm going to do a little bit of it, and then I'm going to do this part, and then you're going to do the blue part. Okay, so here's the idea. Starting from an argument, and let's say I express this argument in English. Who knows what just happened to this pen, but we're going to put it back. There we go. Starting from an argument that is usually expressed in English, because that's math for you, we can end up translating it to pure logic. That's a really important thing to want to do because English is ambiguous. So first step is always translate it to logic by like making your changing the word and into the symbol and, changing the word or into the symbol or for the correct kind of or, right? And we also want to replace each proposition with a variable, all right? So that's important. And then we call it the end result, the form of the argument. So that's a key new term. The form of the argument is just the logic symbol way of writing the same thing. Okay? So here's an argument down here. We're going to translate it to have a proposition for every... we're going to replace each proposition here in English with a variable that stands in for that proposition. We're going to break it down as far as we can, and then we're going to give the form of that argument. Okay? And then after that, we're going to prove it. I'm going to ask you to do that, just like we're doing up here, using the form of the argument. Now, push the symbols around using the rules of inference to do the proof. All right, so here is an argument. So let's give the form of it first. Remember that you have a bunch of hypotheses followed by a conclusion. So here are our hypotheses. I will buy a new car and a new house only if I get a job. Okay, so there's that. I am not going to get a job. Oh no. And I will buy a new house. So I'm assuming all those things. And I'm trying to show, therefore, I will not buy a new car. Okay? So, by the way, only if, that is the this way of the arrow. It's the left to right normal implication. It seems weird, but we'll get used to it. Okay? Only if really means this in logic. If means the other way. Okay? So, let's try and give the form of this. I'm going to come up with some letters to represent these ideas. So, like, what's the smallest idea here? Like, I will buy a new car. That's one idea. And also, I will buy a new house is another idea, right? And then the third idea is I get a job. You see that? And this is like the negation of I get a job, and this is I will buy a house, stuff like that. So let's turn these into propositions. So let's say that P is I will buy a new car. I will buy a new car. Try to make this legible. And let's say that Q is I will buy a new house, because that's another fact, another idea that we're trying to assume. We're going to assume both of those things, right? I will buy a new car. Oh, sorry. Wait, I wrote that already. I will buy a house. Buy a new house. I will buy a house. And then finally, the other thing that we have here is I get a job, right? That's something that could be true or false. Either I get a job or I don't get a job. So I get a job, that's a proposition. I get a job. So those are my propositional variables, and I can use those to give the form of the argument. All right, so this was a bit too long of a line. Let's do it more like this. And then here's the form. I'm going to write it over here. So here's the form of the argument. So I will buy a new car and a new house only if I get a job. So remember, the only if is from here to here. So this is like the hypothesis. This is the conclusion of the implication. So it's I will buy a new car and a new house. So that's P and Q. Only if I get a job. So that's implies, P and Q implies R. Alright? See how I'm translating it like that? That's a bad looking parenthesis. So I'm going to fix that. But that's the idea. That's the form of that first hypothesis. See how I'm translating it into symbols so that I can't mess up as easily. And so here's the next one. I am not going to get a job. Oh no. So that would be the negation of R, right? We're assuming the negation of R. Darn. Unfortunate. And then also, we're going to assume that I will buy a new house. So that's Q. We're going to assume that Q is true. And then we're going to try to conclude, based on all these hypotheses, that, gosh, I want this to look pretty, darn it. So there we go. We're assuming Q, and then finally we're trying to conclude that I will not buy a new car. Therefore, I will not buy a new car. So the negation of P. So that's the form of the argument in symbol form. Okay? Does that make enough sense? So this is now something we can use our rules of inference on. It looks a bit more like these tables. Okay? So look at this table, stare at it, and look at the form of this argument, and see if you can push symbols around until you can prove this. Okay? And use this kind of setup where you name every rule that you say, including the ones that you're assuming by assumption. So give that a try, and then I'll do it with you. So the first step is I'm going to be copying and pasting this onto a blank slide, because that's where we're starting. And now I can see our assumptions and our goals. All right. So kind of the idea is, I want to get like not P out of the deal, and this looks very similar to our last example, right? I have from the last lecture, I have this thing, an implication with an R at the end, and I have the negation of the conclusion. That just screams modus tollens, right? Negation of that conclusion gives you the negation of the hypothesis. So let's start with that. I think that's going to lead us to somewhere fruitful. So I would like to use modus tollens on both of these, so I need to start it off, just like I was doing up here, get everything in order, all right? Be very clear about it. So I need both of these things at once, and I have them both because I'm assuming them both. So I have this, P and Q implies R. I have that by assumption. Make a big table again. By assumption, I know that is true. I'm assuming it. It's part of the assumptions, part of the hypotheses of this proof. And then I have not R by assumption. And then now, I'll give these numbers 1 and 2. I can use modus tollens on, I guess it's 2 and 1. That's the order that wants those in. And that gives me the negation of that hypothesis. So I get for free the negation of this hypothesis, which is this. I get the negation of P and Q. That's the whole hypothesis negated. I get that by modus tollens on 2 and 1, if you want to give the exact order. So I have that. And then this has a negation on the outside of stuff. We don't really like that. That doesn't really allow us to do much. So let's simplify that using a De Morgan's law. All right, let's push that negation inwards. And that gives us not P or not Q. Remember how it flips? That's a De Morgan law. So by De Morgan, I get that. And now I have this and I want this, right? And that's my goal. How do I get not P out of the deal? Well, if you look at this hard enough, there is going to be, there's something here that's very similar, all right? And you have to stare at it long enough, but it's going to be this. I have an OR, and I have a negation of one side. And if I know the OR is true, that means I have this other thing is true, all right? There's a reason for this. And it does look a bit backwards right now, but this is going to be the one that we want to use, and hopefully once you see it used, you'll see that pattern for the rest of your life. All right, so I have this, and I would like to use this. I have the negation of one side, right? I essentially have not Q, right? I have the negation of this side, and if this is true, if I know that this was not true, this side must have been the one that was true, because an OR, I'm claiming if an OR is true, that means at least one side is true. And I know that one side was wrong. I know that this side was not true because I have this, right? Which is the equivalent of the negation of not Q. And through that rule of inference, through the disjunctive syllogism rule, I have that it must have been the other side that was the true side, that was giving truth to that OR. All right. So that's going to take a while to sink in. You'll have to stare at that. But here's the idea. So I want to use this and this. And so the thing that I have the negation of needs to be on which side of the OR? Just to be very pedantic, it needs to be on the left side. The thing that I have the negation of needs to be on the left side of the OR to use this rule, apparently. And so I have the negation of Q, of not Q, so that needs to be on this side. So I'm going to flip them using the commutativity of OR. So this is equivalent to not Q or not P by just the commutativity law for OR. We know that we can flip them like that. And then I also know that I need to get not Q, right? Because I'm trying to use this rule, and I'm trying to set it up so that P is not Q, and Q is not P. It's a little weird. And then this is going to be not Q. I need this as well. I need the negation of this side. And remember that this side is not Q, so I need the negation of not Q. Can I get that? Yes, I can get it from this, all right? So I can get it because I have this by assumption. I know that Q is true by assumption. It's a hypothesis, I guess. I'll just say that it's one of my hypotheses. It's simpler that way. And then I can get not Q out of that, not Q out of that by the double negation rule, right? Double negation, this would go away, but I actually won it this time. Going backwards. I'm running the double negation rule backwards. And now, watch. Now, with this and this, I have the negation of this side, so it must have been this side that was true, using the disjunctive syllogism rule. Okay? So let's try and write this out. So this, I know that not P is true, that's my final answer, by the disjunctive syllogism rule. Syllogism, where well, first of all, it's on a couple things. It's on this guy. Let's call that 3, and then this guy, 3 and 4. And just to make it clear what we're doing, this looks like this, where it has P's and Q's, right? We're saying that P is, for this use of the rule, the P is, in the rule itself, it's not Q. P is not Q for us. And the Q in the example is not P. All right, so just plug that in. It's a little bit backwards, but that's why it works out. We're plugging in Q, or not Q for P, and not P for Q in this rule. And then I have the negation of P, which was the not Q, and that gives me the other side for free. That gives me my not P, which was what I was trying to prove. So we did it, okay? So that's a bit complicated. Hopefully you got like halfway there, all right? It's a bit of a jump to notice that we need this, but this is like one of the few rules with an or in it and some negations, but that's the secret, all right? That's one way to do it. With each example, you're getting more and more experienced, and so it'll come to you faster, all right? So, yeah. That is rules of inference, and using them to prove cool stuff, like involving English. You just find the form first, and now you do the rules with the symbols. You can do similar stuff with quantifiers, all right? There are rules of inference with quantifiers if you want to prove, like, you want to prove a for all. You want to prove that there exist. But it's very, very special. This takes a bit more thought and care, so let's talk about it. So to prove a quantified statement, to prove like a for all, or to prove that there exist, you have to get rid of those quantifiers, which is weird. And you have to remove them. It's like surgery. You have to do it in a very, very important order, all right? You can't make any wrong moves, otherwise you're going to, you're going to harm the proof, okay? So that's a problem. So what you end up doing is you're going to replace the quantified variables, because everything that a quantifier does is introduce a variable that is quantified over. You're going to replace those variables with either an arbitrary element of your domain or a particular element of your domain, depending on if it was a for all or there exists, all right? So here's some ground rules, but this is the key. So just remember this. You're either going to replace the quantified thing with an arbitrary element or a particular element. That's what the variable becomes. All right, it stops ranging over everything at that point. It's just like it has a name now, and you can use it. So first of all, if your proof calls for an arbitrary element, that means that it can't be anything special. It has to stand in for any possible element. So this is going to be the one that replaces a for all. All elements of your domain should work equally well, if you have to pick an arbitrary element for that variable. All right. An example will make this make a whole lot more sense, but I have to say these words first. And then a particular element, if you have to pick one of those, if it's that time, then that one gets to be a special element, and you can pick whichever one you want, which is quite nice. So that's going to end up being a there exists. That's how you'll replace a there exists with a particular element. You just needed one good one. You can pick the best one for your proof to make it go through easiest. And so that's one idea. And then there's also a separate idea of proving a quantified statement, like proving that a for all is true, or proving that there exists is true as a conclusion of a proof. And then there's also a different way of like using that quantified statement as a hypothesis. Just assume that that's true. How can I apply that to get the conclusion that I really care about? All right. There's a huge, huge difference between proving a quantified statement and using a quantified statement, and I'll try to show you both. All right. So when you're proving something, it's the conclusion that you care about. So you have to show that that conclusion is true beyond a shadow of a doubt. But when you have a hypothesis, you can just assume it, like without any thought. Like assume that is true. That's part of your proof. You can use it. So there's a big difference, and hopefully this helps. I'll show you some examples as well. So if you're going about trying to prove a for all, let's say that we have to prove for all x p of x is true. What we do, the way we do this, is that we prove p of a is true. All right, so we got rid of the for all, and then we say that a is an arbitrary element of the domain of p. All right, do you kind of see how this works? And it's going to end up, if you can prove that, you really did prove the for all, because a gets to stand in for every possible element, any generic element of the domain. If we don't assume anything special about that a, then every element must work all at once. Okay, see how that's going to prove the for all, and it also got rid of this, so they can use normal, so that we can use normal rules of inference on what's inside, because usually there aren't any quantifiers inside. Otherwise, we'll chop some more off using these ideas. So that's how that is. So you prove p of a for an arbitrary element a. And so that will work for anyone at once. If you want to prove a there exists quantified statement, then what you do is you prove p of b, let's say, for an arbitrary or particular element b. All right? So if you're trying to prove a there exists an x such that p of x is true, you just need to find one good element. Like, all right, maybe 42 works out, checks out. Then 42 can be your b. That's a particular element. Or just show that it's impossible for none of them to work. Like one must work, I just don't know which one it is. All right? That's a little weird to think about right now, but if you could, there is a way to just show that one good element must exist, and that can be your b, even if you don't know exactly which element it is. All right? So that's how you prove a there exists. And those are used in a completely different way. All right? If you have this as a hypothesis, if you know that for all x, p of x is true, what does that mean? It means that you can say that p of whatever you want is true. All right? Pick any element of the domain, call it a. P of a is true for that a, right? Because you're assuming this. You're assuming p of x is true for everybody. That's how you use it for all. All right? You're assuming p of x is true for all x. So take any element, and we know that p is true for it. That's what we're assuming, right? And then if you have this as a hypothesis, and there exists as a hypothesis, that means you can make p of b. That means you know that there's some element, call it b, in your domain, such that p of x is true. It's not every element. There's just one good one. We know there's at least one good one. All right? There's a particular element in the domain for which p of x is true. Call it x, but we're not sure which one. We'll just give it some name, some random variable name, and move on. That's all we can say about a there exists. Okay? So that's the idea. I think this one's probably the one you're going to come across the most. So like if you have this as an assumption, you're assuming that for all x, p of x is true, and you have some elements of your domain, like you're working with a, you can just plug a into p. If you're working with b, you can just plug b into p. If you're working with c, you can just plug c into p, because you know that p of whatever is true. If these are all elements of the domain, that means p must be true for them, because we're assuming that everyone works. For all x, p of x is true. All right? That's the idea. So hopefully that makes a little bit of sense. This table should make it make even more sense, because this is the process. So here is some silly named rules, but I'll write the normal English next to them. So this is universal instantiation. This is you have a for all in your hypotheses. You're using a for all. Just like that. And so if you have this as a hypothesis, and then you have some element of your domain, whatever it is, you can conclude, this is a rule of inference, you can conclude that P is true for that element, because you know that's true for every possible element. So that works out. On the flip side, if you're trying to prove a for all, this is proving for all, if that's your conclusion, you need to prove this, then you have to have both an arbitrary element of your domain, and you have to use that to prove that P of C is true. Let's say that C is your arbitrary element. You must then prove that P is true for C, and because you made no special assumptions about C, it's arbitrary, it could have been any element, that means P works for all elements. All right? This still probably sounds a bit vague to you, but with examples, I think this will help. But we need to see these slides first. All right, and then this is the same idea for there exists. If you have a there exists in a assumption, this is using a there exists. And so if you know that there exists an X such that P of X is true, that means there is some element, call it C in your domain, C is some particular element. You know that P is true for that C. It's something special. We don't know exactly what it is, but we know that there's at least one C such that this predicate is true for it. All right? That's what it means for there exists an X such that P of X is true. There's some element where P is true for it. All right? Let's see. I do want to say that when you're using existential instantiation, when you're using there exists as a hypothesis, and you're creating this new variable name, it has to be a different name than you've used before. All right? You can't just be like, oh, I have a variable D, and then I'll instantiate there exists X P of X to say that P of D is true. That's a no-no, okay? You can't say that for any specific element, P is true. You don't know which one, all right? So you have to use a fresh variable name when you're introducing a new variable. Like C was something we haven't used before. It has to be brand new and unique, okay? So that's important. That'll come up later, I think. And then finally, to prove there exists, that's called existential generalization. Proving there exists. What do you need? You just need to show that there's some element of your domain such that P is true for it. So here you have some C, call it C, there's some element of your domain, and you've somehow proven that P is true for that C. That means you found one good element for which P is true. So there exists there exists an X such that P of X is true. Kind of loses information when you say there exists. You forget about which one, but sometimes that's all you really need. You just need to know that there's somebody, one good value, such that your predicate is true for it. And that's where there exists comes in. All right? So, with that in mind, here's an example. All right, finally we have an example. Let's prove that this argument is valid. We're going to name each rule that we use. So, this is a bit similar to our other one without quantifiers. So, like, usually the name of the game is to get rid of these quantifiers, all right? Use them somehow. So we're assuming all these things, and we're trying to prove this as well, all right? So first of all, we're trying to prove a for all. Our goal is this, prove that for all X P of X is true. What does that mean? We're trying to use universal generalization at the end, right? We're trying to prove this. So that means we need to introduce some arbitrary element of our domain and prove that P is true for that element. And if we've shown that for that arbitrary element, it could have been anybody, and so it's true for everybody. All right, so our goal for this proof right now, don't lose sight of the goal, it's P of C for some arbitrary element C. All right, and so this is going to start looking less like a table and more like English now, because that's where we're going. All right, so here's kind of the setup to prove this. I need to prove this conclusion. I need to start by creating an arbitrary element of my domain. So let's pretend that C is an arbitrary element of P's domain. Let's see, B, an arbitrary element I think I can write that better, elim of P's domain. All right. And this is part of me trying to do this, trying to use the universal generalization rule. It's the first bit of it, all right? So this is a little part of it, right? Part of using or creating a for all. So it's for all generalization, universal generalization. So that one. And then I still need to prove P of C, all right, for that arbitrary element C. We're getting there. So how can we get there? Now I have an element, call it C. I can plug in, I have all these for alls. I can plug C in for all those x's, right? Because I know for every x, this is true. For every x, this is also true. Well, C is something I could ask these predicates about, all right? I could use, for example, I could use this hypothesis. I could instantiate it with C. I have an element C. I have a for all quantified thing. I can get out that the predicate was true, the inside after the quantifier was true for that element, all right? So I can use it on this. I can use my C on this, plug it in. Because I know that for all x, Q of x or P of x is true. So let's plug C in. So I know that Q of C or P of C must be true because it's true for every x. C is some element of the domain. It works out for that one. It works out for everybody. And I get that by using this for all. I'm using it. That's universal instantiation. All right? I'll abbreviate it like this. This is universal instantiation. Okay? And then also, I have this other guy too. Might as well use it. That's going to be useful for us. I also have that not Q of C is true, right? Because this quantified thing is true for every x. Well, it's true for C then. C is an element of the domain. I know that it's true for everybody. It must be true for C. That's another use of universal instantiation. And so you see I've gotten rid of those for alls. Now I'm working with concrete things. And I can't spell instantiation. Instantiation. There. And now I can use just normal rules of inference, right? This is another case of the disjunctive syllogism. If you go back and you look at this table, I got the or and I got the negation of one side, so it must have been the other side that was giving it truth. Yeah. So, with that in mind, from this and this, it must have been that P of C is true. Okay? So I have that P of C must be true from both of these, all right? And that's disjunctive syllogism that gave that to me. Okay, so there's that one. And then, what do you know, right? Because I'm trying to prove this for all. I have this arbitrary element, I've declared it, and I've proven that P is true for that arbitrary element. I just have proven the for all. Because C could have been anybody. It stands in for anybody. I haven't assumed anything special about C. It could have been any element of the domain. Therefore, therefore, for all x, P of x must be true. And that's me using universal generalization, this rule, with the part that declared and the part that proved P for that arbitrary declared element. All right, let's number those. That's I guess that's 1 and that's 2. Those are the two pieces for universal generalization. Universal generalization with 1 and 2. And that gave us our conclusion. Therefore, beyond a shadow of a doubt, we have proven that this argument is valid. We've proven it for all, using for alls. Isn't that fun? And so the name of the game really is get rid of the quantifiers, because then you could do your normal logic stuff. This just like pretend this is one big thing. This is like P, this is like a Q, or like R and S if you don't want to use P and Q again. That's the idea. Just like find the form of it. Stop looking at the fact that they're predicates. It's just this is true or false, this is true or false. Just push the symbols around. Okay? So that's what we're getting practice with. Eventually, notice how we've been doing. We started with truth tables to prove stuff. We've moved to using these tables and naming each rule one by one. We've turned this a bit more into English. slowly but surely our proofs are going to be paragraphs. All right, that's where we're going. I'm just making sure you understand the symbol pushing before I trust you to write English proofs. Okay, but that's where we're going. So, okay, new example. You try this. All right, prove that this argument down here is valid. It's going to give you practice on everything. So first, take this thing, find the form of it, right? Define predicates, give variable names for everything, define predicates, and express the hypotheses and the conclusion using those predicates. So find like the smallest chunks that you could possibly find, then create the form of this argument, and then use your rules of inference to prove that the form is valid. You're going to have to use the quantified ones, because do you see how there's the words someone and everyone and all that? And then once you get rid of the quantifiers, you'll have to use these normal rules of inference as well as your rules of logic. Okay? So that's the goal. See if you can do it all. So, the domain, because we're making predicates, the domain is a set of athletes on a team. Okay? That's the idea. And, all right, let's say that everyone practices hard or plays badly, or both. So that's like inclusive or. Someone does not practice hard. Someone plays badly. All right, so do you see how there's two predicates being defined here? You got like P of X. Define that to be like X practices hard. And then Q of X is, do we want this to be plays well or plays badly? I guess we always say plays badly. So let's say that Q of X, define that to be, let's say Q of Y. Just to show you don't have to use the same variable name. Y plays badly. It's just this is a parameter, right? Y plays badly. So you got that. And with that, we can generate the form of this argument. All right, so what's the form? We got, all right, this is this domain thing is just talking about the predicates. So this is the actual argument. So everyone practices hard or plays badly. So every athlete, call them X, for all X. Either that X practices hard, so either P of X is true, or that X plays badly, so Q of X is true. So that's your assumption. And then there's someone who does not practice hard, so there exists, right? There exists an X, such that not P of X is true. Someone does not practice hard, okay? Therefore, conclusion, therefore someone plays badly. There exists an X, or Y, or Z, just as long as you're consistent. There exists an X such that Q of X is true. That X plays badly. All right, so that's the form of the argument. Now that we have it in this form, we can use our rules. It looks a bit more like the rules now. We can use the rules to create a proof for this. Oops. Go back. There we go. So let's copy and paste this over here. Put it in the corner. And you got your two hypotheses and your conclusion. And our goal is to just show that this is true, show that this is a valid argument. So show that from the hypotheses, it always follows that this must also be true. Okay? So our goal is to use these two things, right? Because they're hypotheses. Our goal is to use them to create this there exists. So our goal is to create a there exists, so we must use this at the end of the day. We must be using existential generalization. So we need an element of our domain somehow, and we need that P is true for that element. All right, that gives us our there exists. So let's think about that. But do you kind of see, if I forget about all these quantifiers for just a split second, it is disjunctive syllogism all day long. It's like you got that, put it in there. You know the negation on that side means that Q of X gets plopped out, stuff like that. So our goal at the end of the day is to get down to normal logic, get rid of these quantifiers by using them, instantiating them. So I need an element to my domain one way or another for this. How can I get it? Well, I have a for all. I can use a for all like this, but I need an element already. I need an element first to use the for all. So that's not really going to help. So this is not like the first step, which means this must be the first step. It must be to use the there exists. So what does it mean to use the there exists? We instantiate it. If you know that this is true, you get out for free that, oh, there's an element of your domain, and P is true for that element. Cool. So that gives us our element as well. So let's use the there exists in the hypothesis. Let's instantiate it. All right. So there exists an x such that not p of x is true. So all right, let's use this. Let's instantiate this. Let's say, all right, let's see. This is saying that there exists an x such that not p of x is true. Let's call that person, that athlete, such that not p of x is true for that athlete. Let's call them C. Let C be an athlete. I don't know exactly who they are, because the there exists isn't really telling me much about them, but I'm getting out of it for free that not P is true for that C. Okay? And I'm getting all that from both of those at the same time from existential instantiation. Oops. Excuse me. Still not over this cough. So, all right. Existential instantiation gives me all this. And then now I have this C. I have an element in my domain, and I can now use this for all. I can plug C into the for all and get out that, oh, yeah, P of C or Q of C must be true. Excuse me. Okay, so I know that P of C or Q of C must be true. And that's called for all instantiation or universal instantiation. Right? I can get out. I can apply that element into my quantified statement to get out that the inside was true for that particular element. So this whole thing is true for my C. So that is for all instantiation. And then, all right, now I have this guy and this guy. Do you see how I can use a disjunctive syllogism now to get that to get that Q of C must be true? So I got the left side negated, and I have this or. The or is like we're claiming that this whole thing, this or is true. If I know that the left side must have been false, if I know that the or is true, that must mean that the right side was the true part. That's what disjunctive syllogism means. That's what this rule is trying to claim. If I know that the or is true, I know that the left side was false, but the answer was true, that means it must have been the right side that was giving the truth to the whole thing. So, I'm proving now that Q is true for C. Okay? I get that from disjunctive syllogism. All right. And now, from that, I can prove my there exists. Because, what do I need? I need some element of my domain. I need that P is true for that element. And I have both of those. I have an element of my domain. I have that Q is true for that element. So I know that there exists some element such that Q is true for it. In particular, it was C. We kind of like package up that it was C. We lose that fact. But we just need to know that there's one good one. We found our one good one. We're done. So therefore, there exists an X such that Q is true for that X. And that's by this guy. Existential generalization on this fact and this fact. Where are those in our proof? Let's number them. So this is existential generalization on the fact that introduced the variable, so that's 1. Let's call that one 1. And the fact that proved that Q was true for that particular value, for that variable, whatever it really was. We don't really know. But we just know that Q is true for that one thing. So we found one good one, so there exists. There exists somebody. It worked out. Existential generalization with 1 and 2. All right? So that gives us what we're looking for. All right? So this slide, or this set of slides is about logic, this whole chapter, as you're reading it. It's about logic and more symbol pushing kind of stuff, so a little tedious. But where we're going now is to use these facts in a more flowing Englishy kind of style, now that we know the facts. Now we can get away from all this table-y stuff and move towards writing English-looking proofs, and that's what mathematicians do all day long. So that leads us into these slides where we get to have a bit more fun. But we had to do the hard work first. We had to learn like why all these things are true, why all these rules work out, why they're valid. So now we get to enjoy the fruits of our labor. All right. So here's a new set of slides. We'll do a little bit of these, and then that'll be it on proofs. All right. So let's prove all these fun things and see if you can try to find the issue with this proof, because 2 is not equal to 1, is it? So yeah, let's start with just some silly ideas. All right, here's me speaking philosophically for just a second. Please allow me to. And I'm going to try to trick you into liking math, because maybe we've taken a bunch of math classes in our time and we didn't really like any of them. But this class is a math class, and we like computer science, most likely, if we're still in the major right now. So, like, let me try to prove to you that you might enjoy this one, okay? So, proofs, for example, like, everything up until now was, I would say, was not higher math. Proofs are like the beginning of what people like to say, what mathematicians like to call higher mathematics. It's like the cool kids club, all right? And this is also when I tell you that just math in general, math majors and people doing math all day long in like grad school and stuff, they are not plugging numbers around. They're not plugging numbers into formulas and getting out numbers as answers. That is not what mathematics means. And it might be, though, that all the math classes you've taken, even through calculus, might have just been about plugging and chugging stuff into formulas or remembering patterns. That is not what mathematics is, okay? That's more computation. You learn computation in those classes, not really math. So modern mathematics, like from the 1900s onwards, I claim is like art, all right? That's why it has some cool computer science stuff inside of it that we're trying to extract for this class. I would say that modern math, discrete math being a piece of modern mathematics, I would argue that it's beautiful. It's both beautiful, and it has nothing to do with plugging and chugging numbers all day long. We can do math on trees. We can do math on linked lists if we really wanted to. We can do math on algorithms. That's kind of weird. All right, so that's where we're going. That's where you're going in all of your future computer science classes. So once you transfer to a 4-year college and you take upper division computer science classes, you're going to notice you're going to be using all this stuff from this class all day long, which just seems a little odd because we haven't really gone through much in this class, but I promise it's going to get more and more useful as we get going. Proofs, in a very real sense, are kind of like a program. It's kind of like writing a program because it needs to be correct. It needs to be you got to set up your variables properly. You need to return the right answer, right? Proofs are kind of like programming, and programming is kind of like art. So I say that from now onwards, we're kind of we're making beautiful things. We're creating art in this class, all right? So this is me being very philosophical. And I'm going to show you some really cool proofs in this set of slides, ones that will blow your mind, at least one that's going to blow your mind. It's really fun. And I say all this because, I don't know, maybe if I could go back to being an undergrad again, I might major in math and minor in computer science. I'm not sure. I like this stuff a lot, and I hope it comes across in my lectures. So that is enough of me ranting, but hopefully it's starting to convince you, maybe at least a little bit, that even if you hate math, just because this class is called discrete mathematics, it might not be so bad. All right? So, all right. To get into proofs, sadly, with everything in math, you can't escape this. We need a bunch of new definitions. All right, so let's define some things we actually already know, but we're gonna hit it harder because we know about logic now. All right, so here are some definitions that we know and love, and we're gonna use them to our advantage. Okay, so this is an easy one. An integer, call it x, right? A whole number. Call it x is even. What does it mean for a number to be even? Well, how would you logically specify this? A number is even, call it x, if x is equal to 2 times some other integer. Call that k. Does that make sense? It's a multiple of 2. That's what it means to be an even number. You're just spelling that out for somebody. So to convert it to logic, that means, all right, if x is even, that means there exists a k, that's an integer, such that x is equal to 2 times k. Okay? See how we're converting that to math? And this stuff we know how to plug into proofs and use with our inference rules. That's where we're going with this. All right. An integer is odd if it's not a perfect multiple of 2. It's off by 1. There's a remainder of 1. All right? So an integer x is odd if there exists another k. There exists a k such that x is equal to 2k plus 1. So there's a remainder 1 there. All right? That's what it means to be odd. A number, call it r, is a rational number if it's the ratio of 2 integers. So it's a fraction. That's what it means to be a fraction. All right? So if there exists integers x and y such that y is not equal to 0 because you don't want to divide by 0, that's undefined, and r is equal to x over y. All right? So a rational number looks like this. R is a rational number if there exists an x and there also exists a y such that y is not equal to 0 and r is equal to x over y. Notice that a rational number, whole numbers are also rational numbers, like 2 over 1. That's a rational number, and that's just 2, right? So whole numbers, integers, are also rational numbers, but like 1/2, that's a rational number because it's 1 over 2. So you got that. And all right, we've been talking about evenness, oddness, dividing stuff. So an integer x we say divides an integer y if it goes in cleanly, if it's a factor, all right, if y is a factor. If x is a factor. So let's see here. So x divides y if y looks like this. Y is equal to k times x, right? Because you can divide by x cleanly and get some integer result. Okay, so that's that. And we use this symbol to mean that x divides y. So for example, 2 divides 4. That's how you'd write it, because 2 is a multiple of 4. And then 3 divides 12, right? It goes in. 3 is a factor of 12. So all these words, they're more or less interchangeable. So if x divides y, then y is a multiple of x, or x is a factor or divisor of y. That's another way to say it. But all right, let's convert this to math. So x divides y, what does that mean? We're making a definition. That usually implies, they imply each other. It's an if and only if. That's how you make a definition in math. So x divides y if and only if there exists a k such that y is equal to k times x. So that means x can divide into y, and you get a whole number k left over. All right, that's the idea. So that's that one. Primeness, that's important. So an integer n is a prime number. Only numbers 2 and onward could be prime or composite, so it has to be bigger than 1. And then also, that n was prime if it's bigger than 1, and for every positive integer m, if m divides n, then it must have been one of the trivial factors of it. It must have been 1 or n itself. Does that make sense? The only factors of a prime number are that number and 1. Every other one must have not gone in. So this is trying to say that. It's trying to say that, all right, if it has any factors at all, if m divides n, whatever that m was, it must have been either 1 or n. It's nothing other than that. It's not like 2, it's not 3, it's nothing else. So that's trying to say it has no other factors. All right, so n, we say that n is prime if and only if n is greater than 1, that's one thing, and, right, so we can do logical and, n is greater than 1 and, all right, this is going to look a little weird, for every positive integer m. All right, so I have to quantify for every, and for every m that's positive, so if it's positive, that means it's greater than 0. So if m is greater than 0, then, all right, so for every positive integer m, so for all m, if m is greater than 0, then say something I care about now. For any other ones, it doesn't matter. So I'm only considering positive m right now. If m divides n, that's another, oh gosh, that's another implication. Let's put this way over here. Just pretend that we know that this is still on the other side. Come on. There it goes. Come on. PowerPoint and Windows 11, man, hates me. So, all right. Where were we? So n is prime if and only if n is greater than 1 and for every positive integer m. So another way to write that is for all m, we have to quantify over every m, and then we pick out the one we care about. If m is greater than 0, so now we've said everything over here, we know that m is positive, right? We're quantifying over every positive m at this point. If that's true, then if m divides n, then So an inner implication, then either m is equal to 1 or m is equal to n. Then m is equal to 1 or m is equal to n. Close those off. So that's going to take a while. See if you can try and convince yourself that that is what this whole part down here is saying. But that's one way to translate it to logic. And then finally, an integer n is composite if it's not prime. So one way to define compositeness is just say not prime and just use this previous definition. Or you could be fancy. You could do it separately. So if and only if n is greater than 1 and there is an integer m such that m is between 1 and n and it is a factor. All right? Oops, did I mess something up? Yeah. Such that m is between 1 and n and m cleanly divides n. So we can use our division idea all over again in a different way. So n is composite. A composite number has a non-trivial factor, and it's composite if and only if it's greater than 1. So those are the only numbers that can be positive or composite, or sorry, prime or composite. And it's greater than 1, and there is an integer m. So there exists this time. There exists an m. So it's almost the negation of this in essence. There exists an m such that 1 m n, so m is between 1 and n, strictly not equal to either of them, and we know that m divides n. And honestly, this really is the negation of this. It is the opposite. Okay, so just another way to write that. So that's what it means to be composite, and you can use this in a proof. Okay, so it's very important that we convert all this stuff to logic and get good practice with it, because even if we see these words now, we need to be thinking this stuff. All right, that's how you prove things. You have to be very, very specific about it. All right, and it gets a bit tedious with these kinds of definitions, right? You have to be very, very precise, and you have to use things in the right order. So that's why we're talking about it. All right, so let's get started on our proof journey, because now we're going to start writing more Englishy looking stuff. So here, you try this. So this is an easy one. Indicate whether the integer n equals 42, my favorite number, is even or odd. All right, I think you know the answer immediately, right? But use the definition. Show me. If it's even, show me that there exists that k. If it's odd, show me that there exists a k such that that inner thing is true. Prove it to me. So if n is even, show that n equals 2k for some integer k. If n is odd, show that n is equal to 2k plus 1 for some integer k. That's the difference. Show me which one. So you pause the video, give this a try. I swear it's worth it. So all right, I know this is very easy, but this is like our first baby starter proof. N equals 42 is even, and now we got to use the definition of evenness, right? It's even because that number is equal to 2 times some other number, right? Exactly that, and that other number is a integer. N is even because n is equal to 2 times 21, right? And 21 is an integer, and that could be the k, right? There's my one good value. So there exists. I just need one good value. There it is. K is 21 for 42, right? Multiply that by 2, you get what we're looking for. That's why. That is a proof that n, which is 42, is even, okay? Can't be odd. There is no integer such that n is equal to 2 times that integer plus 1. It will never work out. So it is even because of this, and that means it's not odd. Okay, it's a little weird, but that's where we're going. Another very important thing is like remembering what the negation, or learning that what the negation of like comparisons is, right? Have you thought about this before? Maybe you've written enough C++ that maybe this is second nature to you. But what does it mean to like push this negation inwards? What's the opposite of x being greater than 42? What's the opposite of y being less than or equal to negative 100? So let's think about this. If this is a new idea to you, let's think of the number line. Let's say that like here's my number line, and then here's 42. Let's zoom in on 42. I'm trying to take this and negate it. So what's x greater than 42? It's like, all right, it's not 42, but it's greater, somewhere over here. So that's what x greater than 42 is, and then the negation of that is the exact opposite part of the number line. It's x is either 42 exactly or lower. Okay, on and on forever. That's the negation. So that means, what does that mean in a normal comparison symbol? The opposite, the negation of x being greater than 42 is it must be less than or equal to 42. See that? So use the number line if you're ever getting stuck. But that's the idea. What's the opposite of y being less than or equal to 100? What's the negation of that? All right. Again, let's go to the number line. So let's zoom in on negative 100. What's y less than or equal to negative 100? Well, that means it's either exactly equal to negative 100 or strictly less than that. If I'm trying to say that's not true, the negation of that, I'm claiming that, all right, it better be greater than negative 100. Never exactly equal to, but greater than. And that's the opposite. So y greater than negative 100. So that's what it means to create the opposite comparison. Have you done that before, maybe? That's how you can simplify that kind of stuff. Maybe you've done this in programming. So, yeah, it's really just number lines to the rescue. If you negate a less than, it becomes greater than or equal to. All right, and prove this to yourself. If you're negating a greater than, it becomes less than or equal to. If you're negating this guy, less than or equal to, it must be strictly greater than. Greater than or equal to must be strictly less than. If it's not equal, it's not equal. If it's not equal, it's a double negation, then it's just equal. See that? And the reason for that is, of course, like, all right, what's the negation of x equals 42? It's definitely x is not equal to 42. And I think that kind of makes sense too. But this one, this double negation, maybe that's not as obvious. So like, what's the negation of it's not true that x is not equal to 42? It's like a double negation. Let's draw it. All right, x is not equal to 42. What does that mean? Well, here's your 42. It is, well, it's not 42, but it's anything else, anything above and below, right? So the negation, the only thing left in the number line that's not filled in, is 42 itself. So the opposite is x is strictly equal to 42. It's exactly 42. And that should prove it. Okay? So that's negating comparisons. That will be useful to you one day, I promise, sooner rather than later. And with that, before I blow your mind too much and go further into proofs, like this was our first real proof, I would say, let's talk about just proving things and like the etiquette and like what's going on. So of course there's new definitions to end us off. So we say that a theorem is a statement, something that you can prove to be true. All right, it's usually something you want to prove. We call that a theorem. All right, it's something we want to prove and show to be true. And all right, so a theorem is something important. Like a theorem could be that 42 is even. It's something we want to prove. So that could have been a theorem. We could have called it that. And in order to prove a theorem, like what do we do here? We use like a definition. We use some logic. We instantiated a there exists, right? It all worked out. We just didn't say that too much. But that's what was happening under the hood, right? So to prove a theorem, you can do a bunch of stuff. You can use logic, of course. We use a lot of that. You can use any assumptions that you've made in the proof statement. So like there are usually some hypotheses because you are making an argument in your proof, in your theorem. Any assumptions that you make in the proof statement or elsewhere are fair game. And a word for statements that you've assumed elsewhere, those are called axioms, all right? That's when you've assumed something outside of the proof statement. It's just like part of the universe you care about. You take those as ground truth. They're called your axioms. All right. So there's that. You also can use, like you can build up the idea. You can build up all of mathematics with theorems one at a time. So you can use any previous proven statements because you know that those were true. You just proved them to be true a few pages ago. So you can use anything that you've proven previously. And some people really wanted to do this one day, and they wrote a really long book. And like on page 500 is when they finally proved that 1 + 1 is 2. So you can build all of math piece by piece if you really wanted to, one theorem at a time. And you just use as firepower the previous ones. Okay, this is really cool to think about. And then, yeah, finally, at the end of the day, when you're writing a proof, you're proving a theorem, it looks like this. You're assuming, right? Assume all your assumptions. Assume that all your previous proven theorems are true. You don't have to prove them over again because you've proven them once. So take all of these, use them as firepower, to lead to your conclusion. So assume all this is true, use it to prove your conclusion, all right? And then it's just an implication. From then on, you can use logic and all the rules that create implications for you, okay? That's the goal. And that's where we're going in the most part. This is what our proofs will look like. They're going to look more like English than like symbols from now on. And go back to the symbols if it ever gets a little weird looking, because you're really pushing them underneath the hood from now on. Okay, that's what's going on. But logic, the reason we talked about logic first is because we need that. And that's going to be our main firepower that gives our proofs truth. Okay, so that's where I want to stop today, and we will write some cool proofs, some more cool proofs next time.